for the introduction, and thank you very much for the invitation to speak here. I missed the first conference, so it's good that there is a second one so I can participate here. I will speak on something that is at the same time elementary, but at the same time maybe a bit complicated. So, which are Toeplitz algebras associated with semigroups. And this is joint work with Camila Sehnem. So just to remind you, something not working here. Let me remind you that what the left regular representation of a submonoid here means a sub-semigroup of a group that has the identity in it. So when I said submonoid, it's the same thing as unital semigroup. So throughout, I will assume that the P is a submonoid of a group. So P is a semigroup, and it embeds in a group, and it contains the identity of that group. It is not necessary for most of the things, but for some of the things I will be doing, that this group be present, and it simplifies things. So we will assume it throughout. The left regular representation is a map that goes from the semigroup into the isometries of L2 on itself, on the semigroup. And what it does, it just multiplies on the left by P. So L sub P is left multiplication by P. And you take an element of the orthonormal basis, and you just multiply the subindex by P. So LP of delta Q is delta PQ. And then, since you're transforming orthonormal basis elements into orthonormal basis elements, you just have to extend to bilinearity and continuity. And because the semigroup is in a group, it has a left cancellation property, and that means that you get an isometry from this. An isometry, by the way, is an operator that preserves the norm, but it is also characterized by the algebraic property that the adjoint of the adjoint of V times V is the identity. So I see you gave me power to admit people to the meeting. So the object of interest in this context is the reduced Toeplitz algebra, which is the sister algebra generated by these isometries, these left multiplications. And by the very definition, it's a subalgebra of B of L2 of P, so it's a concrete sister algebra. And that makes available all sorts of spatial techniques to study this T lambda of P, this left regular sister algebra of P. And it's very convenient and powerful techniques. For example, there are conditional expectations corresponding to taking the diagonal terms in an infinite matrix and many other things. But so it's very useful, but there's a nagging problem about representations of such objects. And the problem is that estimating the norms of operators is not easy. And if you think of it for a moment, if I have on the right here, when you generate the sister algebra, you have the LPs, you have the adjoints, you have the products, and you have linear combinations thereof. So in general, you have to send a polynomial on the LPs and the adjoints to a polynomial on the target operators V1 through VP. And that norm is difficult to estimate. So it's not clear that a map simply assigning LP to VP will extend to a map from a contraction from polynomials to polynomials. So it may not extend to the sister algebra generated by the LPs. And it's hard to estimate that inequality there. So, and there are famous instances where that has been resolved. Von Neumann inequality is one of them, but it's generally a difficult problem. But on the other hand, if you, instead of having T lambda of P generated by concrete isometries, you have a sister algebra defined in terms of a representation, which means some generators and some relations. Then every time you identify generators that satisfy those relations, then there is automatically a representation of the universal sister algebra with those generators and relations. So one possible approach to study T lambda of P is to try to find a suitable presentation that characterizes it. Maybe not on the nose, maybe that's not possible, but as well as possible. So try to find relations that define up to possibility T lambda of P. So, and that up to possibility is very concrete. It's an amenability type property that P may have, which ensures that once you found the relations, T lambda of P is universal for those relations. And that sometimes happens and sometimes doesn't happen. I'll have something to say about that in a minute. Anyway, so here are three situations which we know from classical situations. One is Coburn's theorem from the late 60s, which is if you take a unilateral shift, that's the left regular representation of the semigroup N, and you take any other isometry V, then you can map the powers of the shift to the powers of the isometry. And that map extends to a homomorphism from the C-star algebra of the shift to the C-star algebra of B. And that homomorphism is an isomorphism if and only if the other isometry that you took is not a unitary, it's a proper isometry. So VV star is not the identity. So that result, is not exactly the way Coburn formulated, but it's equivalent to the way he stated it. So I'll rephrase it in the next slide. Another such universality uniqueness result is Douglas's theorem from the early 70s, which is if you have a subgroup of R and you take the positive cone, so the positive elements in a subgroup of R, and then you take again the left regular representation and then any other isometric representation, any other representation by isometries of that semigroup gamma plus, then that map extends to a homomorphism from the left regular C-star algebra to the C-star algebra generated by the new representation. And that homomorphism is an isomorphism provided, or if and only if, the new isometries are not unitaries. And it's enough to have one, because this group gamma plus is totally ordered. Once you have one of them non-unitary, then they're all non-unitary for P different from 0. So again, that's a characterization of a C-star algebra in terms of a universal property. And then another one slightly different, but along the same lines, once you've reformulated, is Cuntz's theorem. And this is a result that appeared in 81. It appeared after the famous result on ON. It's about the Toeplitz extension of ON. And what it says that if you have the left regular representation and another isometric representation of the free group, the free monoid on N generators, and if you assume that the generators have orthogonal ranges, so that's the first orange condition there is special, is different from the others, then the map that assigns the left regular generators to the new generators VP, it extends to a homomorphism of the Toeplitz, the reduced Toeplitz algebra of Fn plus onto the C-star algebra generated by V. And again, that is an isomorphism provided that something is proper, but here the properness condition is a bit different from the other ones. It is not enough that all these isometries are themselves proper. They have to be proper in a joint way. In other words, there has to be something in the common orthogonal complement of all of them. It's not just that each orthogonal complement is non-trivial. The common orthogonal complement has to be non-trivial. And this last condition here is equivalent to saying, because Vj stars are orthogonal, if you expand this product, you see that this condition is just saying that the sum of the range projections is strictly less than the identity. Anyway, so the three results, the way I put them, they look different. They look similar, but originally they were different, but they are along the same lines. And what they say is that N, gamma plus, and Fn plus have universal Toeplitz algebras, reduced Toeplitz algebras. So on the left here, I have the semigroup. In the first case was P equals the natural numbers with 0 included. And the presentation says they are isometries, and they multiply as a semigroup. In the second, P is the positive cone or subgroup of the reals, and the relations again say they're isometries, and they multiply like in the semigroup. And in the third case, where we have the free group, the free monoid on N generators, the conditions are the same. They are isometries, and they multiply as in the free monoid, but we require something else. We require that if the cones, so if you have words, here's the subset of words that start with mu, and here's a subset of words that start with mu. If those are not intersecting, then the product of the corresponding range projections have to be 0. And it's enough to assume this for generators, and then extends to general words. So provided that we include this extra orange condition here, the trio theorems, they give a universality of the left regular representation in each case. And surprisingly, in the case of the free monoid, the required amenability, which I haven't described yet, holds. And it also says that provided you assume an extra properness condition, there is a unique sister algebra. So the presentation plus the properness condition characterizes the left regular sister algebra, the Toeplitz algebra. So along the years, then people studied this, and I want to single out two significant generalizations. There are many, but I want to point to milestones in the theory. But first, let me say that it's clear that those extra relations are going to be necessary in some cases, like the orange relations that I have. And the reason is that if you just went and took the universal sister algebra generated by two commuting isometries, and you didn't say anything about their adjoints, then the universal sister algebra of two commuting isometries is a very large algebra. It's a non-nuclear sister algebra. This was proved by Murphy, I believe, in the late 90s, 97, I think. So what are those conditions? Let's see, and Nica in 92, and there's also further subsequent work of mine with Raeburn. If you have a subsemigroup of a group, you call it quasi-lattice ordered if it doesn't contain any invertible elements, so P intersection P inverse is just the identity. And anytime you have elements in G, when you take the intersection of the cones, that intersection is either equal to another cone or is empty. And if it's equal to another cone, this element Z is unique because there are no invertibles. So this Z is a supremum of X and P, or least common bound of X and P. So you call those quasi-lattice order. And then the presentation that you want for characterization, for the characterization of the left regular sister algebra is that only consider isometric representations that mimic this behavior. So the behavior of the cones is mimicked by the range projections. So if you multiply two range projections, VP star, and VQ star, you get the range projection of that corresponding Z here, of the supremum of P and Q, or zero. And you get zero when those two cones don't intersect. So Nica realized that if you require that condition, it includes Cuntz's condition for the extension of the ON, and it gives a very rich theory for this class of semigroups, because it characterizes the left regular representation very well, I mean, as well as it can be characterized in terms of relations. But that restricts the semigroups to satisfy this property. There are many semigroups that satisfy this property, but of course there are more that don't satisfy this property. But the theory was kind of stuck until some examples started appearing from number fields, and then some techniques started being developed, and then Xin Li realized what was going on. So he came up with this idea, which was a turning point in the theory. So he said, take any semigroup. Here we're taking subgroups or subsemigroups of a group, but his theory is more general than this. But let's just stick with a subsemigroup of a group which contains the identity. And then he said, for the presentation, take isometric representations of P that preserve the semi-lattice structure of a distinguished collection of subsets of P. So he identified the generalization of these cones that Nica had considered as something he called constructible right ideals. I'll explain in a minute what they are. And when P is quasi-lattice ordered, then these constructible ideals are simply these cones with P times P. So the cones with vertex on the elements of the semi. So let me give you an example of what constructible right ideals are, the Xin Li's constructor. So if you're going to take the left regular representation and going to generate a C-star algebra, at some point you're going to have products. You have the isometries, you have their adjoints. The isometries multiply the right way, and you multiply them. The adjoints multiply the right way, and you multiply them. But sometimes you have an isometry and an adjoint multiplied together. And here I put four: LP star, LQ, LR star, LS. So I take four elements in the semigroup and I multiply four elements in the C-star algebra. And we want to know what it is as an operator on L2 of P. So to compute, use the orthonormal basis to put a number, vector delta sub x, and you multiply on the left by LP star, LQ, LR star, LS. And when the LS meets the delta x, it simply multiplies by S. But when the LR star meets the SX, it wants to divide it. But it cannot always divide it because SX may not be a multiple of R. Well, if that's the case, the result is 0. But if SX is a multiple of R, then you divide and you put delta R inverse SX, because now this R inverse SX is in P. And you continue doing that. Now you have this LP star LQ delta R inverse SX to deal with, and you apply the same logic. The next element, which is LQ, it just multiplies. That's what the left multiplication do. So it's QR inverse SX. But when the LP star meets that vector, it wants to divide it by P. And it is not always possible to divide by P. So if the resulting vector QR inverse SX is not a multiple of P, you get 0. But if it is a multiple of P, then you just divide it by P. So all in all, you get that the original operator LP star, LQ, LR star, LS, delta X is simply multiplication by this group element, P inverse Q, R inverse S times X, provided that X was in the set P intersection S inverse R P intersection S inverse R Q inverse P. Because every time you want to backtrack, there's a cutoff. And this set is implementing all those cutoffs. This is the initial cutoff. You start in P. This is the second one when you multiply by R inverse. And this is the last one. So this set emerges naturally when you multiply an alternating L star L product. And that set, we have a notation for it. We call it K of PQRS. Is equal to P intersection S inverse R P intersection S inverse R Q inverse P. And that's a constructible ideal. So these sets are the constructible ideals of Shinli. They appear when you multiply and divide, and cut off when your division falls outside P. And when it can be performed, the operation multiplies by this group element. And if this group element happens to be the identity, in other words, if that word alpha equal to PQRS is a neutral word, because this multi-fraction Q inverse, P inverse Q, R inverse S is the identity, then here you get the identity, so you get back delta X, but you only get back delta X if X is in the set. So when those words alpha, PQRS are neutral, then the initial operator LP star, LQ, LR star, LS is simply multiplication by the characteristic function as a subset. So this replaces the cones. This is the idea that Shinli abstracted from the left regular representation. And he said, let's make that our focus. So what are constructible right ideas in general? Well, in general, for each K, you take a word of length K on P. So you take a sequence P1, P2, up to P2K. In reality, it's the length 2K because we have alternating signs. And you define alpha dot to be the multi-fraction or the left quotient, which is the first one has an inverse, the second one doesn't, and you alternate inverses. So it's P inverse, P, P3 inverse, P4, etc. You define alpha tilde to be the reverse word. And the set K alpha, which is a generalization of what we just saw before, you start with P, then you, starting from the end of the word, P2K inverse, P2K minus 1, P intersection, etc. So you run through the whole sequence of increasing multi-fractions until the last one, and the last one is just alpha tilde dot, which is the reverse left quotient. This describes all constructible right ideals. Optionally, you can include the empty set. Sometimes it appears by itself, sometimes it doesn't. You can include it, it doesn't hurt. So, and the property that it has, the set of constructible right ideals is a semilattice under intersection. So the intersection of any two is not obvious from the word presentation, but if you concatenate two neutral words, the constructible right ideals intersect. And the set become much longer, but somehow there's cancellation, and you just get the intersection. So once you have this set J of constructible right ideals, then Shin-Lee defines a semigroup C-star algebra, which he calls C-star sub S, I suppose for semigroup. And it involves some notation. So let me introduce this notation here that says that if you have a map, just a map into a C-star algebra, and the word alpha, then the W dot alpha is the alternating product again with adjoints and elements, adjoint and elements. So WP1 star, WP2, WP3 star, etc. And the definition of Shin-Lee is that the semigroup C-star algebra is universal, generated by a family of isometries and a family of projections, and the projections are indexed by the constructible right ideals. And the isometries multiply as in the semigroup, so it's a semigroup of isometries. If the right ideal empty is there, then the corresponding projection is 0. And the W dot alpha, this is the most important one, W dot alpha is equal to ES whenever alpha dot is neutral. So alpha dot is the identity, so alpha is a neutral word, and the corresponding constructible right ideal is S. So this ensures that when you take neutral words and you take products like this one, W dot alpha, they will behave like a semi-lattice of projections. And because it behaves like a semi-lattice of projections, it controls what's happening in the algebra generated by the W dot alphas, and it gives you a satisfactory theory. In fact, in many cases, the C-star algebra characterizes the left regular C-star algebra T lambda of P. For example, when P is totally ordered, it does the job. When it's a quasi-lattice order semigroup, it does the job. And in other cases, for example, AX plus B semigroup of an algebraic number field, it also does the job, which is not quasi-lattice order. So in particular, if you do L dot alpha, we computed already, it's 1K alpha. We computed for the PQRS, but it's a general fact. And that map gives you the 1K alpha satisfy Shin-Lee's conditions, so that gives you the T lambda P as a quotient of C star S of P. But Shin-Lee observed that the restriction to the diagonal, so if you look at the diagonal, which is a C star algebra generated by the neutral word, so V dot alpha for alpha dot equals E, and the diagonal in the left regular is this one that we computed already, 1K alpha for alpha dot E. That map is injective only if these projections have a property. They have to be linearly independent, which seems like a reasonable assumption, but it's not always true. So if independence fails, the C-star algebras are not isomorphic, simply because the diagonals are not isomorphic. So that was an observation of Shin-Lee in about 10 years ago. So this led to a definition of independence if the set of 1K alpha, 1K beta, so the characteristic functions of constructible right ideals are linearly independent, then we say that the semigroup satisfies independence. And in that case, C star S characterizes T lambda of P. Equivalently, if you can write K alpha, so a constructible right ideal coming from a word alpha, if you can write it as a union of other constructible right ideals, then one of those has to be K alpha itself. So you cannot do this unless, you cannot get K alpha by taking the union of constructible right ideals unless you put K alpha as one of them. So that's independence. And of course, there are semigroups where independence fails, and Shin-Lee provided an example. I want to run through this it's an easy example, and it's worth fix the ideas. Just take the semigroup, which is N, 0, 1, 2, 3, etc., and take out 1, throw it away. The remaining sigma is a semigroup. It contains the identity, so it fits in the theory. You can have principal constructible right ideals, which are N plus sigma. So you go from N, skip the next one, and then keep going. That's a constructible right ideal. But there are some constructibles that are not principal. For example, if I do K of 3, 2, 2, 3, then you're led to compute, I just follow the formula, and you get 2 plus N, which does not skip the 3. So this is not a principle, but it is the union of two principles. So if you think of it, K, this 2 plus N is only missing the 3, which is not here. But if you add 3 plus sigma, then you get the 3. So this 2, the union of these two is that one. So independence fails because they're not equal, but the union is equal to 2 plus n. So for this Easter algebra, the diagonal is not equal to the left regular diagonal, and the Easter algebra sub S is not equal to the Toeplitz algebra. So the upshot of the interpretation of this is that C star S of sigma is not a good universal model for T lambda of sigma. It just fails already at the level of the diagonal, and therefore, and this is a very simple abelian case, so there's no amenability involved here. More interestingly, perhaps with Sehnem, when we proved our results, we started looking at other failures of independence, and we managed to prove that independence fails for all AX plus B monoids of non-maximal orders in number fields. Here, when I say order in a number field, is a free full rank subring of the ring of integers in a number field. So if you don't take the whole full ring of integers in a number field, take a full rank subring. That's called an order, and it fails independent in an essential way. So we define a universal sister algebra that takes care of this condition of failure of independence. So what we do is we take elements. We don't impose any algebraic relations on the elements, except to say that the identity is mapped to 1. T dot alpha is 0 if K alpha is empty for a neutral word alpha. So if a word alpha gives you the empty constructible right ideal, then its T dot has to be 0. If two words give you the same constructible right ideal, then their T dot alphas have to be the same. Those alternating products with T star and T have to be the same. And if you have a situation like this, where K alpha is a union of K betas, this could be a failure of independence, then we require that the T dot alpha minus T dot beta, when you multiply them all together, you get 0. So this product here says that there's nothing in T beta, in T alpha that is not in the T beta. So we replicate the property K alpha equal to the union of K betas with projections in the C star alpha. And in fact, so some consequences, a bit surprising perhaps, is that once you impose these conditions, in particular just T3, T3 says that T dot alpha depends not on alpha, but on the constructible right ideal of alpha. And once you know that, TP becomes a semigroup of isometries. There's no assumption that these are isometries. There's no assumption that they multiply the right way. But if they depend only on the constructible right ideals, because of properties of the concatenation of words, this becomes a semigroup of isometries. And the T dot alphas become a commuting family of projections. And they satisfy Shin-Lee's condition. In fact, if you cut at T3 here, T1, T2, and T3, they constitute a presentation of simplified presentation of Shin-Lee's C star S of P. So we're adding T4, so we're getting a quotient of C star S of P. In particular, you notice that T alpha equal to T beta, T dot alpha equal to T beta is a particular case of this one when the set F, the finite set F, only has one word, because then T4 restricts to T3. The only reason we spell them out this way is so that we can cut off and say up to T3 is C star S, and then past T3 is T sub U. So more interestingly, if P satisfies independence, then you look at this condition here, and let's interpret T4 when P satisfies independence. It says, that K alpha is equal to the union of K betas. Well, if P satisfies independence, then one of the K betas has to be equal to K alpha. And then by T3, the corresponding T dot alpha and the corresponding T dot beta are the same. So this product is 0 because one of the factors is 0. So T4 is automatic for when independence holds. And that means that since T4 is automatic when independence holds, then TUP is equal to C star SP. So we're getting the same C star algebra Shin-Lee when independence holds. But when independence doesn't hold, we have an extra condition. And the extra condition is good because in general, we get the same diagonal. So the DU corresponding to the diagonal generated by the T dot alphas is isomorphic, canonically isomorphic to the D lambda in the left regular. So this diagonal has an action of the, so the semigroup, up to now, I haven't said anything about the semigroup except that it's a sub-semigroup of a group, but it could be the whole group, or it could contain a significant group inside. And if you define that P star to be the invertible elements in P, so this is the largest group contained in P, then there is a unitary action of that group that acts on the diagonal simply by conjugation. So gamma U of L dot alpha is simply LU, L dot alpha, LU star. You can write it with words too, so you see that that lands back in the diagonal. It's a little bit complicated because our words are all even, so you have to add extra elements. Anyway, that gamma, in fact, is the restriction of a partial action of G. So P star is a subgroup of G, and in fact, there's a partial action of G on D lambda defined by the same condition. And the cross product, the reduced cross product of that partial action, of that action by P, is a subalgebra of the reduced cross product of the partial action by G. So this P star acting on D lambda is a subalgebra of D lambda P. And the theorem that we proved is a faithfulness theorem, and it says that for that every non-trivial ideal of T lambda of P has non-trivial intersection with this cross product D lambda by P star. So in other words, a representation of T lambda is faithful if and only if it's faithful on the subalgebra D lambda cross product by P star. So this was a theorem of Shin-Lee when there are no units. So when P star is trivial, this was known. And we extended the result for semigroups that have significant groups of unit, as is the case, for example, of semigroups coming from number theory. So out of this, we can build a universality uniqueness theorem. We have to assume that this amenability or weak containment is satisfied, and then we use the result to characterize faithfulness of representation. So suppose that there's a condition, the conditional expectation. This is the map. It's a canonical map that goes from the TU lambda to the universal diagonal. Suppose that's faithful. This is a sort of amenability of a certain partial action. And suppose that you have another collection of isometries satisfying T1 through T4. Then you can assign LP to one of those isometries, WP, and that map will extend to a homomorphism of C star algebra from T lambda P to the C star generated by W. And that is an isomorphism, provided the restriction to D lambda cross product by P star is an isomorphism. So that's just the characterization of faithfulness that I just showed you. So it is satisfactory in the sense that it's completely general. It works for every subsemigroup of a group. But it focuses your attention on a cross product by P star, not on just the diagonal, which is a standard, better known results go all the way down to the diagonal. But those are not general. So, but however, for a class of monoids, we can decide uniqueness based just on the restriction to D lambda. In other words, we can identify a condition on the monoid that tells you that you can go down for a simplified condition for faithfulness on just D lambda. And those are, we call them TF, TF or topologically free. So a monoid is TF if every time you have a unit that is not the identity, and you have a collection of proper constructible right ideals, there is something that is not in their union that is moved away from itself by the unit. So the units act on the cones, UTP is sent somewhere else that is not equal to TP. It could intersect TP, but it has to be a different cone. So the theorem says that if you, again, have this weak containment condition, that is a faithfulness of the conditional expectation from TU of P to DU, and P is contained in G, and it satisfies this condition TF. If you have another collection of isometries or of elements satisfying T1, T4, then you can map LP to WP. That extends to a homomorphism from T lambda to C star W. And that will be an isomorphism if and only if W is so-called jointly proper. And jointly proper is just a small modification that works for constructible right ideals of that condition that we had to impose in the case of Cuntz's theorem from 81. So we say that a family of elements is jointly proper, satisfying T1 through T4 is jointly proper if the product of the orthogonal complements of the W dot alphas is not zero. That's for every finite collection of neutral words. So there's something in the common orthogonal complement of all those W dot alphas. If you think of the left regular representation, this is, for example, this is satisfied, for example, because the vector, the identity, the delta of the identity, because these W's are, these W alpha dot alphas are not the identity because the constructible right ideal is proper, then they will all kill that vector at the identity, the vacuum vector, but the identity won't, so you get non-zero. So let me give you a quick sketch of at least part of the proof. Because you have a faithful conditional expectation, there's a standard argument that tells you that the universal one is isomorphic to the left regular. So the universal TUP is equal to the T lambda P. That's a square argument, a commuting square argument using faithfulness of conditional expectations. So that means that we can use the universal property for T lambda of P. So T1 through T4 is an actual presentation of T lambda of P. And the pi W map will exist. And then, because of the main result, faithfulness of the representation pi W, it boils down to faithfulness on the restriction to the subalgebra D lambda cross product by P star. So we need to show that D lambda cross product by P star is faithfully represented whenever W is jointly proper. So what we show is that our TF semigroups are precisely those semigroups for which the action of the units on the diagonal is topologically free. And we also translate jointly proper condition to stating that pi W is faithful on the diagonal. So this is another translation. We're still not at the cross product. We're still at DR, but then we use Archbold and Spielberg's characterization that says that the action of a group on a compact Hausdorff space is topologically free if and only if representations of the cross product are faithful when they're faithful on the diagonal. So that allows, by this result of Archbold and Spielberg, we can move up from DR to the cross product and complete the theorem, the proof. How am I doing with time?
You're doing fine. You have another 7 minutes, and if you want a little more.
Yeah, 7 is fine, thanks. So let me talk about something else, because I know when I say, when I mentioned the result of Cuntz from 81, I know many of you thought, well, no, that result is from 77. The result from 77 is about ON, and ON is in a way is more interesting C star algebra, and it appeared first. But the result from 81 is about the Toeplitz extension of ON. So let me go to the ON, to the analog of ON. And that those they exist in every case. And with Sehnem, this is actually what triggered the whole project. In her thesis, she defines something about covariance algebra associated to product systems over semigroups. And when I saw that, I realized, well, if you can do that, then somewhere in there, you have a definition of a general Toeplitz algebra. And the covariance algebra is the boundary quotient of the Toeplitz algebra. So let me go through just a definition here of what foundation sets are. So it's a finite collection of constructible right ideals. The union is contained in a right ideal, but so we also require that if you take something in P, there's an ideal in R that intersects, whose cone intersects some R. So it may be that the union is not all of S, but everything that is in S and not in the union has something bigger that is in the union. So the cone of every element based on S intersects some R. So somehow the R's, they cover the horizon. They may not cover the ground, but they cover the horizon. If S is not the union itself, in other words, if T4 does not apply at S, because if S is equal to a union, then you have T4 that tells you what the projections are. But if S is not 4, then we can apply a new boundary condition, which we call T5, and it's the same condition as before. The W dot alphas minus W dot betas is equal to 0. The product is equal to 0. But now this is applied to a different kind of set. It's applied to the sets K betas, where the union of the K betas is contained in K alpha, but with the extra property that something in K alpha will eventually intersect something in the K betas. So these are foundation sets. So we define them based on Sehnem's covariance algebra. So essentially, we looked very carefully to her definition of strong covariance condition, and we identify there these boundary relations. Now, we can state them without reference to the covariance algebra. The foundation sets that are not proper, in other words, the foundation sets where equality holds for S is equal to the union of the R's, they're already included as relations in T4. So these relations T5 are new because the foundation sets are proper. And what we saw, this is something that we suspected, is that if you put T1 and T5 together, so you put all these relations, including the proper foundation sets, that's a maximal set of relations. Maximal in the sense that if you took an extra relation of this kind that is not already there, the quotient of the TU is going to be trivial. So you're going to kill every element because you kill an isometry. And because of that, you get a theorem for what we call a full boundary quotient. So to give you a little background for the last two items, the partial action of G on the diagonal it is a property of this kind of system, has a largest invariant ideal, which we call d lambda 0. That also can be identified using Sehnem's covariance algebra. And it corresponds to the smallest non-empty closed invariant set delta of omega p of the spectrum. So du is a commutative algebra, has a spectrum. That spectrum has smallest, not minimal, actual smallest non-empty closed invariant set. And the theorem is that all these algebras are canonically isomorphic. One is the covariance algebra of the one-dimensional product system over P. I don't have much to say about this, but this is something that existed already. The universal Caesar algebra with this presentation I just gave you. And then the full partial cross product, these d lambda 0 G. This, in some sense, this full partial cross product will be an Excel type of boundary. And similarly, you can replace these d lambda 0 by its by continuous functions on its spectrum. So because of the equivalence between 2 and 1, this covariance algebra is the quotient of TU by the boundary relations for proper foundation sets. And we think of them as a full boundary quotient. And there's another boundary quotient, which is reduced. You can view it as a reduced cross product here, so there's a boundary quotient d lambda p, which is the cross product, the reduced cross product of the boundary action. And for that, we show that every proper ideal of the boundary quotient, the universal boundary quotient, is contained in the kernel of the canonical map. So you can never see inside the kernel of this map, but at least you know that if the possible ideals are contained in the kernel, then the partial action will give you a G-simple quotient. So the partial action is topologically free. And then we have a characterization purely in terms of the semigroup. If you take two different elements in the semigroup, there exists some other element in the semigroup S, such that P sends the cone SP to a different place than it sends that T sends it. So the translations by T and by P become orthogonal. So the cone SP is sent into this joint cone from TSP. And so this third condition characterizes the semigroups that behave as Fn in Cuntz's ON paper. So this is intrinsic to the semigroup. And also there's right angle arc in monoids from early work of mine with John Crisp, and also the AX plus B monoids of rings or ring sister algebras of Cuntz and of Lee. So these are boundaries that their boundaries have the property. And as a consequence, if you have one of these semigroups, the boundary quotient is purely infinite simple because you have topological freeness. So what we have is, in a sense, a characterization, a purely infinite simple sister algebras by presentation associated with semigroups. So together, the characterization of the Toeplitz algebra by a presentation and the corresponding uniqueness and universality results are, until the next iteration, are the ultimate word on sister algebras generated by isometries. Because, okay, maybe I shouldn't say that too loud, because we are assuming that these monoids are contained embedded in groups. If one were to remove that property of embedding in groups, then one gets into a different territory, because I haven't said anything here, but the coaction of the group is instrumental in many places. Anyway, I think that's all I want to say. Thank you very much.
We thank you very much. You made it this time virtually, so I hope soon you'll make it physically too here. Do we have questions? Marcelo has already board behind.
Answer questions.
Can I ask a question?
Sure. Yes, sure. Go ahead.
Actually, I have two questions. First question is on your definition of the sister algebra of a semigroup. You described the definition by Xin Li using constructible right ideas.
Yes.
But I think later he had an improved description using the enveloping inverse semigroup of a semigroup. And then you take, so what's the connection between, I think when the constructible right ideas satisfy the independence condition, then you get the isomorphism between the full sister algebra and the reduced. Now is that, now what's the connection if you use the different definition of the full sister algebra?
There is okay, so you can define, you can recover this sister algebra using an inverse semigroup. This is work that he did partially together with Magnus Norling. And there still remains the problem that if the semigroup does not satisfy independence, you're still not getting our universal TU.
Yes. Mm-hmm.
Yeah, there's still a gap there in the diagonal. And
but is it the same gap or a different gap?
This is a good question. I don't know if that answer. I don't know the answer. I think that may not be known. I think yeah, it is a very good. It's a sharp question. I don't know that. I looked into this and I realized there's still a gap. I don't know if it's the same gap. I suspect it is, but I do not know. Certainly, I don't know. I do not know if it is known.
Bruce says that it's the same gap.
I mean, that's quite possible. Okay, a second question. You know, a good example for a semigroup that does not satisfy the independence condition are the semigroups that are associated with toric varieties.
Yes.
Now,
yes.
do these satisfy your TF condition?
This is in my plans, but I haven't. I know exactly where to look, and I don't have an answer right now, but I hope that in a finite time I will, because I'm looking at that.
Yeah, that would be nice to know.
I've been looking at the one-dimensional case. I have a student looking at that, but my plan is to look at the multi-dimensional case for sure. This class of examples you mentioned, and the orders in number fields are extremely interesting classes of examples to analyze. For the orders in number field, we have verified the condition TF, so we know they have purely infinite simple quotients.
Yeah.
But we haven't looked at the toric varieties yet.
Well, it is semigroups from toric varieties. I mean, the Toeplitz algebras associated are also very closely related to Toeplitz algebras considered by Douglas and such people a long time ago.
Yeah. The semigroups that you mentioned have several classes of representations. In a way, I'm looking at just the smallest one, which is the representation of L2 of itself. But look at them represented in the larger ambient n to the d. You can identify invariant subspaces at all levels. And one interesting question is to look at the subsequent quotients. I suspect they will appear looking at that. It is indeed a fascinating class of examples, but I'm sorry, I have no results to report.
Okay, thank you.
Yes,
good luck.
Yeah, thank you for the question.
Any other questions to Marcelo? Well, you got your good questions. You were right. You also have thanks in the chat. Make sure you see them. So can we have some applause to Marcelo? Thank you.